dear visitors and the participants of our workshop. Edge Computing Workshop is a peer-reviewed international computer science workshop focusing on research advanced and application of edge computing, a process of building a distributed system in which some application as well as computational and storage services and provided and managed by central clouds and smart device, the edge of networks in small proximity to mobile device sensors and end users. The goal of those is to bring together researchers and participants from academia and industry working on edge computing to share their ideas, discuss research work in progress, and identify new emerging trends in this important emerging area. Okay, so Sergey Alexeyevich, do you want something to tell us?
I don't want to say something. I would like to have a fruitful, happy workshop.
Thank you. We invite the first our author of the article is Alexander Andreev, and his work increasing the speed of digital image processing in edge devices with limited computing resources. Alexander Andreev, please.
Yes, good afternoon. Thanks.
We don't
Please
see you.
wait a few seconds. I would like to present to
We hear you, but we don't see you. Oh, and you don't see me? Okay.
But we do.
I'm sorry.
Are you ready? Oh, yes.
Yes, I'm ready.
But we don't see you.
I would like to present to you a presentation on the topic increasing the speed of digital image processing in edge devices with limited computing resources. Nowadays, digital image processing is one of the fastest growing technologies. AI is often used in digital image processing to recognize objects and detect their motion. AI uses machine learning during image processing and requires high-performance computing. At the same time, IoT and devices have limited power supply capacities and computing resources. The most energy-intensive operation is data transmission to a wireless environment. Therefore, the choice of digital image processing method depends on image characteristics, specific application needs, available computing and energy resources. The purpose of this work is to develop a digital image processing algorithm for object motion detection that can be implemented on edge devices with limited computing resources. In practice, normalized cross-correlation, NCC, is most often used as a statistical method to estimate the similarity between two consecutive frames. The equation for calculating the NCC is given on slide. To compare two images, they are divided into blocks of a certain size. The NCC algorithm calculates the brightness correlation between pixels of each blocks for two consecutive frames. If the calculated value is less than a defined threshold, then the blocks in the corresponding images are considered different. Light areas indicate differences between the images, while dark areas indicate where they are the same. We propose a digital image processing algorithm for object motion detection that requires fewer computational operations than the NCC algorithm. The absolute difference of the average brightness AD/AB algorithm calculates the average brightness value of pixels in blocks. Equation 1. Then the absolute difference of the average brightness for each blocks of the current and previous according to equation 2. After computing the absolute difference of the average brightness, the motion detection condition for block K is evaluated according to equation 3. Images in block are different if the calculated absolute brightness difference value exceed a certain threshold. We will call this block active. For the practical implementation of both motion detection algorithms, the ESP32CAM module with the OV2640 camera was used. This module has a small amount of internal memory, namely 0.52 megabytes. The total computing performance is up to 600 dry stone million instructions per second, but about 150 DMIPS is spent on data transmission in the wireless environment. For testing, a camera resolution of 320 by 240 pixels was chosen. To increase the speed of mathematical operations, it is also advisable to choose an image in grayscale format with 255 brightness levels. The detection matrix has a size of 16 by 16 blocks. The size of each block is 20 by 15 pixels. The memory of the microcontrollers stores the current and previous frames which are used for computing. The camera position remained unchanged during testing. To simulate movement, the palm was moved in front of the camera. It is necessary to verify whether these algorithms can be applied to motion detection. The main task is to estimate the time each algorithm spent determining the similarity between two consecutive frames under the same conditions. The results of the NCC algorithms are presented on the next slide. Part A contains the NCC values in the absence of motion. As can be seen, most values exceed 0.9. Part B shows the results in the presence of motion. The NCC value decreases for blocks where motion is detected, dropping below 0.7. The next slide shows the results of the AD/AB algorithm. Part A contains the AD/AB values in the absence of motion. The absolute difference of the average brightness between blocks was treated as 0 if it did not exceed a certain threshold, which was set to 10. Part B contains the results in the presence of motion, where, as can be seen, all values exceed 10. At the same time, errors in detecting motion in the frame are possible even in a static image due to random image noise. To reduce the probability of false decisions, it is advisable to conclude that motions present in front of the camera if the number of active blocks exceed 2% of the total number of blocks in the frame. In our case, the number of active blocks equals 5, given that the total number of blocks in the frame is 256. As the test showed, the AD/AB algorithm correctly detected motion even with a small movement of a palm across the camera. As an example, the next slide presents the time intervals in milliseconds and the number of active blocks for both algorithms. As you can see, the time required for one iteration of comparing two frames does not exceed 10 milliseconds for the ADAB algorithm. For the NCC algorithm, the execution time for one iteration does not exceed 105 milliseconds. When moving a palm across the camera, the number of active blocks in the frames may change. The next slide shows the application of the ADAB algorithm in IoT project. As is known, almost 25% of the total computing performance of the microcontroller is spent on processing network protocols and data transmission to a wireless environment. The practical implementation with sending photos to Telegram Messenger demonstrated the possibility of using the ADAB algorithm for motion detection in IoT project. In summary, while both algorithms are effective, ADAB outperforms NCC in processing speed. This makes it is optimal solution for IoT projects using edge devices with limited computing resources. Thank you so much for your attention.
Thank you for your interesting report. And now we invite all of us to ask questions. Who want to ask the questions for Alexander Andreev? Valentin, please.
Yeah, I suddenly lost where is the hand the hand side on the bar. Thank you very much, Alexander, for your good presentation, and it's an interesting field of application. So that's I have a couple of questions. You already started to respond one of them, but I still want to elaborate, especially for the case. Let's imagine that you are looking at the same car, like in your example, and we are just having a very hard rain, like pouring rain. So you have really the drops which are flying in front of the camera. What would you advise in this case to do with the algorithm, and what would be the suggested threshold?
Alexander Andreev, we don't hear you.
Yes, I hear. Thank you for your question. I think the camera, the main is to ensure the same camera setting to compare the processing time of the both algorithm. The camera setting do not affect the estimation of the possibility of the reducing image processing time using the proposed algorithm. Our camera is sorry. The image processing speed is independent of lighting conditions. And this camera does not have an infrared backlight. For our research, this was enough. In the future, we maybe choose another camera.
Understood. So you suggest to use another technical device instead of like correcting the algorithm to detect which object is moving and which object is stalled. Because, for instance, if I want to look at my car, which is comparably bigger than the size of the drops which are moving in front of it, potentially algorithm can still do it. But okay. And another question is, you mentioned that it is not sensitive to light. Does it mean that you convert always to the grayscale when you analyze with the algorithm?
I got it. Thank you for your question. Grayscale require few level and sorry. Could you please repeat the question
Yeah.
again?
In your response just to my previous question, you mentioned that the camera is not sensitive to the light. So, for instance, the sunset, sunrises, and clouds will be ignored. Does this mean that for feeding the image to the algorithm, you convert the color image into the grayscale?
Okay. Increasing the camera resolution reduces the frame rate. Increasing the camera resolution also increases the number of pixels in the image and the amount of memory required to store it, thereby reducing processing speed. However, this issue requires further research.
Understood. Then probably that's it. Thank you very much for your answers.
Okay, thank you for your
You're
questions and
welcome.
your answers. Maybe someone else want to ask the questions? Okay, thank you for discussion, for your presentation, and now we go to the next presentation and next speaker. Next speaker is Anatoly Kalgin, Tatiana Petrenko, Olena Petekop, and Olga Pronina. And presentation AI-supported autonomous systems, EDA technology for designing feeling AI. Olena Petekop, yes, I right?
No.
No?
Anatoly
Oh,
Kargin.
okay, yeah, you are welcome.
Yeah. Let me sharing my screen. Okay. Is okay with the screen?
Yes,
We see your screen.
Yeah, yes. Hello, everybody. Our team from TU University with pleasure present report on new model of the artificial intelligence, feeling artificial intelligence. Not so long ago, we dreamed about perfect AI, but now we are surrounded by generative AI that provide us with service we didn't even think before. It is service in the internet. 1,000 robotic laboratory worldwide united to create general robotic brains. It is hybrid AI based on the generative AI and combine it with pre-trained set of different skills that robots have already been learned. This service is in the real physical world. Feeling artificial intelligence is a hybrid AI for small robotic application, supporting robot mission in autonomous mode without powerful cloud computing facility. Response making engine based not on LLM model, it is based on the cognitive model borrowed from the simplest living being. This approach was proposed by me and has been developed by our team over the past 15th year and is now in progress. The purpose of our present report is devoted to the event-driven architecture technology for design, feeling artificial intelligence application. To clarify what is feeling artificial intelligence, let's pretend a robot services the order to make and deliver a coffee to the customer. It has knowledge about recipe, and this knowledge can be present in the semantic structure, semantic knowledge. But to perform the order, robot uses a lot of sensor data. Until today, there has been a gap between two paradigms, data from sensor and knowledge presented by words. The problem is how they are combined. We compare three possible ways. Symbolic based on the LLM approach, the semantic knowledge extended by the new node presented current value of sensor in symbolic form obtaining from fuzzy logic system. Fuzzy logic system on the base of numerical data send the term of linguistic variable. The such extended knowledge structure fits the LLM model. But uncertainty and lack of the input information LLM overcomes using the general pre-taught knowledge instead of the rely on the specific of the current situation. Next, numerical approach based on the artificial neural network. It has the same disadvantage, and in addition, it isn't transparent what is the necessary requirement for the autonomous systems. Feeling artificial intelligence is a hybrid model that combines these two approaches. We may call this approach as two-in-one, or we can consider the structure from the two perspectives. First, it is a semantic structure, but only it is parameterized due to the new model of knowledge granular. Each node in this picture structure is presented by knowledge granular, including the sensor data. From another point of view, the structure supports the continuous processing of the event stream generated by sensor, with the aim to computing the internal meaning of the knowledge. Event-driven architecture hides the problem of aging data. Back to the robot making and delivering coffee. Pretending that the robot put in coffee, pours the boiled water in, and milk, but the sugar is over. While it goes to the storage room, looking for a sugar, come back, put it in, and the time is over, and the boiled water is cooled down. The robot brings a coffee to the customer which doesn't satisfy the good quality. This violation generates uncertainty. The knowledge granular model must take into account the such uncertainty as shown in this slide by red color. The external meaning of knowledge granular is the semantic definition used in traditional knowledge graph, but it is also have specific parameterization. As you can see, there is parameter new red depicted. It's aging rate. It plays an important role. It opens the possibility of realizing the feeling artificial intelligence on the base of event-driven architecture. The internal meaning of knowledge granular assess the degree in which input data present in the current situation correspond to the external meaning of the KG. We defined the fuzzy certainty factor as a fuzzy number with Gaussian membership function with two parameters. Alpha is traditional certainty factor in traditional theory, and beta is time which use a crucial role in the aging, calculated aging. Knowledge, the fuzzy certainty factor actualizes the contribution of the different events obtained at the different times in the whole situation presentation. In our model, knowledge is presented by a set of response prototypes. Response prototypes is the structured set of knowledge granula. Each circle, it is knowledge granula, divided into three components: sensory template, response making, KG, and action template. The feeling artificial intelligence knowledge base is shown in this slide. It is a structured set of knowledge granule that support event stream from the sensor to actuators. When it is processing, the emotion, attention, and the drive models help overcome uncertainty, make a response in unknown situation by clarifying and tuning parameter of response making KG. From the logical perspective, feeling artificial intelligence is a multi-layer structure of knowledge. So the first step of ED technology is a convolution of this model into structured set of knowledge granule as shown in this part of slide. In the next step, it is transformation of this flat structure in the event-driven architecture components. We used for this simple set of rules, as you can see on this slide. And as a result, we obtained the only three table where is present all knowledge about application which is designed. And finally, it is setting up of software for event-driven architecture. We used a prototype of software that reflects the specific of the feeling artificial intelligence model, and it was developed by our team. And we tested different components of the feeling artificial intelligence of the different autonomous application. In this paper, we present an autonomous garage complex serviced by the wheeled robot that check the state of the automatic garage door. And our conclusion, and thank you for your attention.
Okay, we thank you for your interesting reports, and we invite all of our authors to take the part of our discussion. Valentin, please.
Yeah, thank you very much, Anatoly. It's really an interesting discussion, and when I read about feeling, that's always something which is really inspiring, because artificial intelligence, that's the subject which is more about like reactions and probably filling the gap. A couple of questions. You spoke about the robots applications. Have you applied this for any type of prosthesis, like smart prosthesis, which could react to a specific environment, to specific object, which the person which is having like no hand or whatsoever can adapt to it?
Unfortunately, no. Our all equipment which we used in our laboratory in university, it is a wheeled robot with a different sensor system. Sensor, we try maybe more than 20 different sensor combined together and used for decision making, but it was only wheeled robot, not arm, not any humanoid. Yes, we have one humanoid robot, but it's toy, not real.
Understood, but looking at the algorithm, that's another question. So potentially, if you are using the idea of like having the granular and like applying your intelligent algorithm, how do you educate? I mean, how do you select the granular to infuse and which you just avoid to add? How do you do the refactoring of the knowledge granulars which you infuse into your robot?
No, technology, I may separate your questions in two parts. First, it concerns the designing step, and second, how the robot adapt to the current situation. In the first phase when we design robot application, we need to choose the mission. What mission must do robot? After that, if you can all performing mission without any interface, ideal variant you create, it's not problem. If you have may use the approach like in the fuzzy logic. If describe situation, then you need to do something, and then this part facts which you use in the part if or of, we can not simply transform in the knowledge granular, parameterize. It's another of the question. You need to know how parameterize it. It's publication in our publication in our paper before. But when we design the first step and the robot began facing the new situation, when we didn't before introduce granular, then play, it's very important, I underline this, they play a role our model of cognitive model, attention, emotion, and drive. Attention, emotion, and drive, it's algorithm to turn it knowledge granular to take decision which has before robot don't face.
Thank you very much,
Anatoly. It's special algorithm. It too published it in our previous work. It's published material before.
Thank you.
Okay, thank you. And we have another question from Alexander Andreev. Alexander?
Thank you. I think that your presentation are very interesting and up to date. I have a question. Is it required to use any cloud service in your project?
No. Its main principal position, it's autonomous robot which may perform your missions without cloud service.
Thank you.
Okay, thank you. Thank you for interesting report and your questions and answers. And now we invite the next speaker of our program is Natalia Kulikovskaya, Vitaly Alekperov, Karsten Henke, Artur Timenko, and Tatiana Dichuk. And his presentation, Development of Hybrid Cloud Fog Architecture for Real-Time IoT Analytics. Vitaly Alekperov, please.
Yeah, I'm here. Do you see presentation?
Yes, we see
Yeah,
presentation.
that's nice. So for the first, good afternoon, colleagues. Today I wanna present scientific research about development of hybrid cloud fog architecture about real-time IoT analytics, and I want to start with the concept overview. The concept of IoT systems is finding wide application in various fields, from healthcare facilities and smart home system to specialized robotics laboratories. Recently, there has been a steady trend toward implementing IoT solution in the industrial sector to control, monitor, and predict work processes. In the context of production facilities, warehouses, and server clusters, monitoring dynamics parameters such as temperature and vibrations, which can change rapidly, is critical. Timely collection and analyzing of this data is essential for preventing equipment failures. In scenarios such as pharmaceutical warehouses, requirements shift towards maintain a stable microclimate like temperature and humidity, despite the lower dynamics of change in such systems. Trend analytics and long-term trends forecasting are critical task for ensuring products safety and minimizing business risk. The difference in case studies create specific requirements for system response speed, making the development of a hybrid fog cloud architecture is priority. The modern semiconductor market, represented by solution from NVIDIA, Intel, and Apple, has provided access to high performance, compact computer power, making such system affordable even for small business. Like monolithic models that operate exclusively in the cloud on the local nodes, our proposed architecture minimizes data transfer latency between the edge and fog layers. Local processed at the fog level allowed for significantly cost optimization. Firstly, it reduced peripheral requirements. There is no need for microcontrollers with redundant memory or expensive communication models to manage data queues. Secondly, relying solely on cloud platforms like Azure is often uneconomical for small business due to the overhead of or provision functionality. For computing allows for the use on local resources and open services, making the solution more flexible. This research examines the HX Foundry platform as a software foundation, as well as possibility of developing custom local processing systems. The implementation of hybrid architecture is demonstrated using a pharmaceutical manufacturer example. The system supports the full processing cycle from scale data collection and digital noise filtering to the holes monitor and data buffering before sending it to the cloud to final analytics. The edge level hardware is based on TAL 220 load cells, which is widely open on conveyor lines for higher precision calibration and product screening. Since the sensor produced an analog signal to a 24-bit HX711 converter is used on conjunction with it. The gateway is ESP32 microcontroller with VROOM32 modification chosen for its built-in Wi-Fi and Bluetooth wireless interfaces, as well UART protocol support, ensuring stable data transmission to the fog layer. The microcontroller ensures fast and stable data collection from all sensors for transmission to the fog layer, which will be regular personal computed local in the same room. UART is the fastest communication protocol, but in our study, we will use HTTP and transmit data in JSON format to demonstrate that even a wireless connection to a local fog node is faster than sending data to the cloud computing. HX Foundry will serve as a fog computing platform, offering several advantages over its competitors. Its capabilities and customizable allow to cover a wide range of functionalities to solve various business problems and requirements. Each module will operate independently, but still share the same computing power, allowing for rapidly data transfer from one container to another. However, if any module fails, a data queue will be created, allow it to restart it without data loss or interrupting the other modules. For example, using the core data module, we will continuously collect unprocessed data from sensors. If a subsequent filtering model fails and restarts, in queue will be created in core data modules, but the data will be not lost. The Edge gateway layer cannot provide this functionality as a general task sufficient memory and multi-thread data processing capabilities. The non-relative InfluxDB database will serve as the data storage platform, as it, like the rest of our architecture, is designed for adaptive operation scenarios. This database provides the ability to store data both locally and in the cloud. Alternatively, we can continue to divide the responsibilities. For example, all data older than 1 day will be sent to the cloud and deleted from the local storage. This approach allows us to reduce the cost and simplify the architecture for the hardware layer, which, as we know, very often requires repair, upgrades, and administration. For example, the device service module allows to create device profiles. This provides incredible room for systems capability. By adding any number of devices of the same type to the hardware layer, we define the format, data type, and text will exit. They allows us to narrow the input data streams, which also helps to minimize latency. Since we register device profiles by describing them in .yaml files, this allows for flexible replacement, upgrades, or duplication for nodes. The result is a hybrid architecture, high file fault tolerance, high throughput, and low latency, customization, and ability to adapt to changing operating conditions, as well as capability determined solely by the business owner's budget. In our study, the hardware cost $61, while the Fog computer node and platform were free. Regarding to the cloud layer, InfluxDB offers a free plan sufficient for small private businesses and also offers expansion options. The Grafana platform is free. Compare it to Google IoT Cloud or Microsoft Azure, we saving 98%. While this platform offers enormous computing power and extensive functionality measuring just one parameter across multiple use cases, and often not financially optimal for small business, or is in our case, we measure in just one parameter across multiple use cases. For this research, that's all. Thanks for your attention. I will wait for your questions.
Okay, we have a question. Valentin, please.
Thank you very much, Vitaly, for presentation. That was insightful, and I also worked a lot with pharmaceutical industry and questioning about the weight, right? And the total end-to-end latency, which you stated, is 156.23 millisecond, with the throughput exceeding 450 messages per second. For which specific process was this benchmarked in your work?
That's nice question. Thanks for your question. I'm tested on two different environments. For the first, it's two scales based on TL220 sensors, which have a very big range of noise. So the input data, like from one scale, is 6 to 10 per second non-filtered information about weight. Because in university laboratory I have a pure budget for testing, I'm also implement Python algorithm to simulate 3 or 4 scales to implement fiction throughput and latency. So I'm receive almost the same results on the simulated and the real experiment.
All right. Thank you very much.
Okay, thank you. Who, someone else want to ask the questions? Anatoly, please.
Thank you. Am I right, as I understand, you said that you don't use cloud computing, sorry, cloud facility for computing statistic. Oh, I'm something confused.
Thanks
In
for your
your
question.
report, in presentation, I see that you didn't use cloud facility for computing statistics.
Yes, we use the cloud platforms only for view infographics, transfer infographics to the table or view trends of the information because any cloud algorithm will be have a higher latency that the if we use a fog node because in our research we use independent modulus which provide very good results for small business task, and any cloud algorithm cannot provide a result for saving money for the business.
Thank you. But in your application, how do you think what percentage is computing computing statistic and all another computing task in our application? For me, it's maybe most very big percent computing statistic. Oh, I don't write. It's your
In
opinion
our
only. In your application, yes, in your application.
in our case, we our input data very rapidly changes. In pharmaceutical use, it's weight on the scales. For example, in other cases, in data centers, it's temperature for video cards or CPU, and providing collection and statistic of this data is very hard for local fog nodes because we don't any business don't have very big budgets for store in local servers. It's cost maybe thousands of dollars. If we use only to transfer data, we can use more budgets cases which cost a few hundreds of dollars.
Thank you, Mr. Thank you.
Okay, thank you for your. Oh, we have one more question. Petrenko Tatiana, please.
Okay. Hey, everybody. I have some maybe small question. You say something words about fog level of your application. You use Grafana, but it's a cloud platform. Why you say that is fog computing?
Thanks for your question. I'm said that for the fog node we use the platform HX Foundry. That's one of the famous open source and free platform which have the microservice architecture. We have independent modules for collection data, filtering data, transfer data, and local short-term store. That means we can that platform communicate with with the other models with the lowest latency. Grafana used only because the non-relative InfluxDB database very easy implementing with Grafana, because if we can make a user-friendly interface without a lot of settings, like we use this in the folk nodes, we create a lot of YAML configuration for each type of devices. The Grafana in the cloud can implement for 15 minutes if we have already API token from database.
I agree with you about Grafana, but the question was about fog computing. It's very interesting level right now for discussion because nobody can criticize what is this fog computing, what resources are using in fog computing. It looks like cloud computing. Understand? Thank you for your answer.
Thanks.
Thank you for interesting discussion. Okay, if we have no questions, we go to the next. Our speaker is Dmytro Karnaukh, Maria Tyagunova, Galina Kiricek, and Ravil Kudermetov. And his presentation, research of wireless data transmission protocol parameters for high frequency IoT systems based on video cameras and leaders. Please.
Just a moment. Can you see my presentation?
Yes, we do.
Thank you. Good afternoon. And today I would like to talk about wireless data transmission protocol parameters for high-frequency IoT systems based on video cameras and leaders. Nowadays, video traffic is a key component of Wi-Fi. There is a steady trend toward ever increasing demand on communication channel bandwidth. High-frequency IoT system using cameras and lidars generate large amount of data and require stable wireless transmission even under intensive operation condition. In such condition, traditional wireless protocol settings do not always ensure predictable network performance, as they are designed for general scenarios and do not take into account the specific of high-frequency sensor data streams. IT node performance depends on combination of protocol parameters which interact in more complex way in high-frequency conditions than conventional network scenarios. Without optimizing these settings, the system may lose stability or do not provide the required efficiency. The goal of this work is to develop an optimal approach to analyzing and optimizing wireless data transmission parameters in high-frequency sensor nodes. The object of this study is a model of high-frequency IoT system node with video cameras and lidars operation our wireless Wi-Fi data transfer protocol. The model uses a single unidirectional channel protocol IEEE 802.11 AC standard. The model defines the key parameters that affect system behavior under load: frame interval, data arrival intensity, packet size, number of segments, and CSMA CA configuration parameters. The frame rate is determined by frame rate interval, and the total packet-oriented traffic depends on number of segments into which a single frame is divided. At the MAC layer, transmission is performed according to the CSMA-CA scheme with the possibility of varying the parameter of the minimum and maximum contention windows, the RTS-CTS mechanism, and the maximum numbers of retransmissions. The architecture of high-frequency IoT system node is built as serial pipeline, including sensor module, an intermediate storage buffer, a data segmentation unit, and wireless transmission module. Sensor generate fixed frequency frames, and they arrive in a buffer, smoothing the input variation and align the input stream. Segmentation unit divides each frame into constant length packets. The network adapter forms make frames according to access protocol configuration. This model simulates the behavior of real Wi-Fi system under high load, which is typical for video cameras and LiDAR streams. Simulation study was carried out in the NS3 simulation environment using video camera and LiDAR streams with fixed frame sizes, 3 packet size options, and 3 medium access configuration. For system simulation was selected 4K 60 FPS camera mode with constant video bitrate 35 megabits, frame size 600 kilobytes. Low channel LiDARs with data compression have about 150 kilobytes frame size, and segmentation was selected as 300 bytes for strong fragmentation, 900 bytes for intermediate option, and 1500 bytes for minimum number of segments. For video stream with a video interval of 8 milliseconds, the maximum load is observed, which leads to significant increase in average delay, jitter, loss rate, as well as the number of collisions and retransmission attempts. Increasing frame interval to 16 milliseconds significantly reduces the frame arrival rate and improves all metrics. In the case of LiDAR systems with frame interval values of 50 milliseconds or 100 milliseconds, system operation in stable transition. Delay and jitter remain low, losses are in the tens or hundreds of %. Number of collisions are minimal. This figure shows depends of the system operation on the frame interval parameter. Dynamic demonstrates that increasing the frame interval reduces the load on the MAC layer and improves transmission stability for both video sensors and LiDARs. Although the video stream demonstrates much higher sensitivity to this parameter. The study of the impact of packet size shows that the degree of frame segmentation determines the relationship between throughput, delays, and loss rates. Using 300 byte packet size leads to a significant increased number of segments, which increases overhead costs, increases queue length, and increases likelihood of collisions, resulting in the highest average delay and jitter in the video stream among all the options studied. Switching to a 900 bytes packet size significantly reduce overhead and stabilize transmission. Latency decreases, loss decreases, and throughput increases. Increases packet size to 1500 bytes provides lowest overhead and the highest effective throughput, but at the same time increases sensitivity to channel errors, losses, and delay fluctuations. This figure shows the depends of the channel operation on the packet size parameter. Results show that optimal packet size is 900 bytes, where balanced compromise between overhead and transmission reliability is achieved. For LiDAR traffic, the impact is weaker due to low frame rate. Analyzes the operation of different CSMA-CA configuration demonstrates that MAC level parameters significantly affect system stability under high load condition. Aggressive setting with low CVIN values reduce channel access time, decreasing average delay, but at the same time cause a sharp increase number collisions, retransmission attempt, and losses. This makes aggressive mode unsuitable for high-frequency video streaming. Conservative configuration with RTS-CTS significantly reduces number of collisions and retransmissions, ensures minimal loss and maximum stability during the video streams. This figure shows compression of MAC channel configuration. For LiDAR traffic, changing the MAC parameters has much weaker effect since the stream parameters a small load. A consolidated assessment of the three parameter groups shows the access protocol optimization is impossible without considering the interaction between frame interval, packet size, and CSMA/CA configuration. For video streams, the best balance between delay, loss, and throughput is achieved with frame interval 16 milliseconds, packet size is 900 bytes, and MAC configuration with RTS-CTS. This provides stability and minimal loss with reasonable jitter. For LiDAR, the optimal parameters are less critical due to low traffic intensity. The simulation research demonstrates how changes in frame interval, packet size, and CSMA/CA parameters affect the operation of the sensor channel under simulated condition. For given characteristic of streams, decrease frame interval leads to an increase and load and corresponding fluctuation in delay, jitter, and loss. Variation in packet size show differences between strong and weak frame segmentation modes. Changing CSMA/CA configuration affects system behavior during heavy video streaming, while LiDAR data provided the less sensitive. Therefore, wireless protocol parameters should be optimized comprehensively, as changing one parameter can either improve or worsen other metrics. For future work, the developed model can be improved by including adaptive bitrate, implementation valuable capabilities of IEEE 802.11be standard, such as multi-user and multi-channel scenarios. Thank you for your attention.
Okay, we thank you for your interesting report, and we have a questions from Valentin Yanchuk. Valentin, please.
Thank you, Dmitro. That was really insightful. And the first question is, the study focuses on the single channel 802.11 AC environment. How would you expect result to change in the multi-channel or 802.11ax Wi-Fi 6 setup?
I guess multi-channel can add about 30% for stability and decrease losses. But I think multi-channel need more investigating to smart control between priority channels. Because, for example, video stream can be work with one channel with priority, for example, high, but control stream maybe will work for unpriority channel, and LiDARs can be investigated how the behavior will be with multi-channel configuration. And I guess now produced a lot of devices, IoT devices with old standard, supported old standard. And real configuration of node will use old devices and new devices, and need some intelligent system that will control all devices and prioritize them with channels.
Thank you. And again, development of this question and your answer, based on findings, what practical recommendations would you give to an engineer configuring the Wi-Fi network for a robot with an autonomous vehicle equipped for both a 4K camera and LiDAR sensor?
I think LiDAR sensor have more critical data. For example, if the object moves,
Mhm.
And video camera can make mistakes about motion detection, for example. And robot, I would like to use robots with lidars and video cameras than only video cameras. But these sensors are more expensive.
Thank you very much for your answer.
Okay, thank you. And we have another question from Roman. Roman, please.
Thank you for presentation. Yes, I want to ask question about packet size. Yes, you described that packet size 900 bytes as the optimal packet size. Was the possibility of adaptive real-time packet size adjustment based on channel condition considered?
Yes, but for this work, I investigated dependencies 3 Wi-Fi parameters in complex for stability video and ladder streams. And for real situation, I think packet size can be changed adaptive. Maybe for noisy channels, need to reduce packet size, and for clear channels, system can be enlarge it.
Agreed. Thank you.
Okay, thank you. And we have a question from Anatoly. Anatoly, please.
Oh, thank you. Short questions. You said that you prefer LiDAR sensor compare the video camera. What kinds of the LiDAR sensor did you use? The two-dimensional or three-dimensional?
Two-dimensional.
It's more you prefer with video.
So for my experiences with video cameras has too much mistakes if we will use video images as recognized video images to analyze and make decisions. LiDARs can more stability fact that object is present or not present, object is moving or not moving. And even cheaper LiDAR is more powerful system, makes system more powerful.
Thank you very much. I am share my opinion with you. Thank you. Thank you.
Thank you.
Okay, thank you. Thank you for your presentation, for your discussion. And we now go to the next speaker and next presentation. It's resource efficient view shot wildlife classification using Dino V2 and weight fuzzy ensemble from Kristina Ляпіна-Гончаренко, Олександр Stepanik, Diana Загородня, and Pavlo Bykovy. Are you here? Pavlo? Pavlo, we don't hear you. Oh, yeah.
Yes.
Pavlo, we don't see a presentation and we don't hear you.
Okay. Can you hear me?
Now we
Oh,
can.
yes.
Okay, now. Okay, 1 moment. And now, can you see presentation and hear?
It's loading. It's still black. We
Oh,
see the
yes.
presentation, not full screen.
Not for 1 moment. Now is okay.
Now that's good.
Yeah. Okay. Excuse me. I don't know why it happens. So problem is that biodiversity monitoring, if we need to have automatic systems to recognize animal species in nature, and camera trap data, they generate too many images, and people cannot label each manually. And finally, this is that the camera can be placed in the places without internet or cloud, and so it should be some part of information should be processed directly on the devices. So the key challenges, the first is that this type of classification is called fine-grained classification, where we have a lot of visually similar species, which is hard to distinguish. And next point is it's called few-shot problem, where we have not big amount, 1 to 5 training images. And as I said before, age constraints that devices are not powerful, RAM limited, and no GPU, and so on. Therefore, it was proposed such hypothesis that we can use powerful pre-trained features combined with lightweight classifiers, and it can overperform traditional fine-tuning approaches under resource constraints. So it was proposed such architecture for such kind of hybrid classification. So first part is using of Dino model as a frozen self-supervised vision transformer. Then which is building feature embedding vectors, and next using of two classifiers, k-nearest neighbors and prototype-based classifier, and finally using of weighted fuzzy ensemble to get the result. So such classification strategy has two complementary approaches. First is that KNN is sensitive to noisy embeddings, is unstable, and has distribution shift. So prototype based is based toward dominant classes with more support samples, and to combine those two approaches, it was proposed fuzzy ensemble. So if two classifiers agree, the prediction is accepted. If they not agree, the higher confidence and decision is based on the confidence levels. So here is presented what data set. So it was used CAP, BERTS, and mini ImageNet data sets to testing and for training. So here is a sample for testing for synthesis occurring for robustness testing, and comparative performance for classification of 5-shot scenario. And so we can see that proposed method give good result, good data that can be used. Also, when we compare provided approach, provided my method with other one. So it shows also good accuracy and results. So in case of this K-short approach, yes, so it can be seen that when we have from 1 till 5 sample, we have rapid increase of accuracy. So as much, so this amount of samples, yes. So when let's say we have from 10 till 20, it increase, we still have increase, but not so rapid. And bigger amount of samples, we still have increase, but not so rapid. Therefore, this approach with 1 to 5 short is good. Say it can, it has, let's say, way for life. Yeah. So finally, that such provided result, it shows good few short accuracy, top 1 accuracy, and in case of requirements, it don't need a lot of RAM, and also speed is calculated near 30 milliseconds per image. And so it can be deployed in some edge device. So final results, conclusion, and thank you for your attention.
Okay, yes, thank you for your presentation. And we have questions from Valentin. Valentin, please.
Thank you, Pavlo. That's very insightful work. Very nice. Birds, that's wonderful. Quick question. Didn't you think about like recognition of, for instance, like butterflies? And how much work you need to add to the current development?
So let's say for now it was everything was trained in the birds data sets. Yeah, so we need to switch from birds to butterflies. Yeah, the data sets. And let's say if we let's say switch to this, we can as let's say it will not change rapidly because approach is similar, that classes seem similar to each other, because let's say it's hard even when human can distinguish between two butterflies. Yeah. So but it is possible. Yeah. So it was possible to do such work without not very rapid update.
Yeah, that's why I ask about butterflies, because I mean, with birds, that's, I mean, similar problems. But still, the architecture caches feature embedding into both training and test images. What is the main computational advantage of caching approach on an edge device?
Main computational advantage of using it on edge devices, yes?
Correct. Cache mechanism. So why do you necessarily need to cache?
So not to let's say not to send all data what was made by camera. Yes, so to reduce.
You mean for storage? Okay,
for storage,
I understand.
Yes.
Yeah, I was just probably recognizing more cache, like if you are pre-caching something, not to ask additional images, etc. And I thought for IoT, that's probably not that important. And the last question. The camera trap images are often low quality, and sometimes you probably need to also take it in the night. And as I already asked for other presenters, in the rain with emotion or blur, how that may affect the quality of the Dino V2 feature embedding.
Yeah, quality, let's say everything depends on the data set what you have. And for night pictures, we need to have night data set and so on. So it's let's say very critical for the available data set. So the quality, we didn't make such tests, but quality will be, accuracy will be not so high.
Understood. Thank you
Yeah.
very much for the presentation, for the answers.
Okay, thank you very much.
Okay, thank you. Maybe someone else who want to ask the questions? Okay, if you have no questions, let's go to the next our speaker. It's Andriy Shvaika, Dmitro Shvaika, and Volodymyr Artemchuk, and presentation LLM-based multi-agent framework for IoT solutions generation in Thinkbot.
Good afternoon, everyone.
Hello.
You hear me well?
Yes, we hear you.
Before I will begin, I'd like to apologize. Unfortunately, I don't have a web camera today available, so I will be presenting without video. I hope this will be not an issue.
It's okay, but we don't see your presentation.
Yeah, I will share it. Give me 1 second.
We see the text file.
Yeah. Right now you probably see a presentation, yes?
Correct.
Yeah, give me 1 second. Okay, so I'm ready to start. Today I will present our work on integrating large language models into IoT platform engineering. Specifically, how we built a framework that transforms the natural language descriptions into functional IoT solution inside the ThinkBot platform. So I want to start with the problem. So designing an IoT solution is hard, and you need domain expertise in data modeling, event processing, access control, dashboards. Basically, know the power of platform you used, and all of this has to be configured manually, and it takes significantly time and knowledge of the platform. So now large language models are incredibly good at understanding requirements and reasoning about system design, but they are stochastic. They can hallucinate, produce inconsistent outputs, or violate platform constraints. In production IoT, where structural correctness and reproducibility are critical, you can just let an LLM generate configurations and hope for the best result. So our goal was clear. Our goal was clear, is to find a way to transform natural language system description into validated executable IoT platform configurations, and do this reliably and deterministically. So our answer to this was a schema-driven generative framework, and the key architectural insight what was called the bridge. We designed the system to bridge the stochastically of LLMs with the strict platform level constraints of IoT infrastructure. The core principle is simple but critical. We separate reasoning which happens during design time, from deterministic execution, which happens during deployment. The LLM thinks, reasons, propose, but it never directly touches the running system. Everything it produces is validated against the strict JSON schemas before it's allowed to proceed further. The framework operates with a single tenant of existing multi-tenant ThinkBird platform. Now I want to talk about the technical side of that. So our framework was built on Java 21 ecosystem with the Spring Boot enterprise-grade stability. And I should note that since the paper was written, we are actively migrating it to Java 25, and a lot of other improvements was made, and I will talk about them in the end of the presentation. For the multi-agent orchestration layer, we use a customized fork of library called LangChain 4G. I want to say why it's customized. We added several improvements to the library, and that was the reason why we was forced to create a fork. First, we add a strict JSON control. We inject per request JSON schemas via custom annotation to force AI output to be predictable and parsable with an 99 precision. Sometimes it still makes mistakes, but we are working on improvements every day. So second, it's important issues that we found there. There was no thought signature preservation in that library, and this was critical because we have kind of assistants that we're calling a chat assistants, and one of that. So we have two assistants, like business analytic. We call it business analytic and planner assistant, and they share the same persistent chat history. And when LangChain 4G library merges messages, the default implementation loses that chain of thoughts reasoning traces. Since both agents read from the same conversation, we had to modify the message reconstruction logic to preserve the exact structure of each AI message, so one agent's reasoning doesn't get corrupted or misinterpreted by the other. And the third is improvement related to caching of system messages for each assistant used in our framework to foster interactive design session. For the LLM model, we use Gemini Flash, which balances reasoning power with the low latency needed for interactive workflows. Now I want to talk about the generation pipeline that we have in our system. We basically divide it into 3 stages, where the stage 1 is deterministic initial configuration. This is where natural language requirements are transformed in a strictly typed configuration blueprint. And each intermediate reasoning step produces structured artifact that is validated against predefined schemas, JSON schemas, before the pipeline proceeds. On the second stage, which is optional, it's like a stage where probably I will show you that on an image. The stage 1, it's where we write natural language description about what we want to create. And in this deterministic initial configuration on the stage 1, in case the requirements is not fully clear, the system may ask 3 clarifying questions and provide some assumptions about the solution we want to build. After answering these questions, as you can see, we answer them simply with like vehicles, speed, battery limit, ignition status. It's for question number 2. And for the third question, we said all listed items, where they ask what we want, for what we want to do that. And after we answering this question, we are going to a state where the BA assistant actually trying to parse the requirements and trying to build first like BA requirements that will be set to a non-persistent assistant to deterministically create entity profiles, create alarms, create calculated fields or metrics. And finally, when all of this is done, we are getting results like this. Actually it's like an overview that the user should approve before we going to a next step. And here is where we have a stage 2. We can write some prompt for improve or edit something. For example, in this solution we have created a fleet like vehicles, and there was 2 zones that used as one as a restricted zone and another type as allowed zone. And this we have 2 actually way to show that blueprint. First one, it's a table view, and the second one, it's showing this as a schema. And then if we want to do some improvements to existing table or schema, we can always write some prompt as we do on this stage number 2, where we ask to add additional zone, call it no parking, and trigger the alarms if vehicle is inside that zone. On the slide, I have decided to show on this slide, I have decided to show the schema view because it's directly shows that now we have a no parking zone asset added, and then like we can go to the next step and start generating dashboards. So the system is built in a way that like once we click the button, go to a dashboard manager, we immediately starting designing a dashboard based on that blueprint solution descriptor that was created on a previous step. As you can see, the loader indicator is displayed, and it says that estimated wait time is around 30 seconds. The actual generation involves dozens of parallel calls orchestrated by our sync pipeline. And as a result, we see 3 role-based dashboards created. Basically, 3 descriptors of a dashboard that we will create once we will hit the create solution button. But on the screen, I'm showing only one of them. Why we have 3 dashboards created? Because on the previous step, we generated 3 roles of users that will be used in our solution. It's like technical user and solution administration dashboard will be created for him. Fleet manager and fleet management dashboard will be created for that role of user, and fleet monitoring for dispatcher user. Each dashboard has a detailed description of its states, widgets, and navigation, and the user can review this, regenerate if needed, or proceed to create the solution by hit the create solution button. Once the create solution button is basically hit, we go to a determinist, sorry, to once we hit this button, we are going to Java-based orchestration of creating the creating the system entities based on finalized descriptors and finalized descriptors of AI entities that was created during the stage 1 and stage 2. Stage 3, where we generate the dashboards. And once the installation completed, we see the deployment summary, where it's showing like demo data that was created. We generated like AI users to show how each dashboard will be look like if you will log in as that user. Also, you can see devices that was installed for evaluation of a solution, and critical point here is like that we try to use the LLM only in a design, while do the deployment fully in Java to reduce the hallucinations risks. And actually what we designed it gets the result that like what we designed it, we actually deploying. Here's the result of a deployed fleet management dashboard, where we can see that there was alarms created. We can see the list of vehicles we have and see on the map the after-generated demo zones, like no parking zone, restricted, and allowed zone, which is a big green rectangle that we see on the screen. Here is another screenshot with another result of generated dashboard for operational monitoring and alarm validation. And as a conclusion, I want to say that our plan was, I think, completed. We designed it that LLMs will be best in design time and not use it as a runtime decision makers. This was the key takeaway. Second is that by decoupling generation from execution, we guaranteed zero hallucinations in the deployed solution. What the LLM produces is validated at every step, and what gets deployed is deterministic and reproducible. Third is that dramatically lowers the entry barrier. A domain expert who knows nothing about IT platform configuration can describe their needs in natural language and gets a complete working solution. And now I want to add important note that a significant amount of time has passed since this paper was written, and the framework has evolved rapidly. We do a huge improvements in the last 4 months, and the system now contains over 120 additional or totally AI assistants classes and over 400 prompts and schema files. Some key developments since the paper is that yes, we migrated to the Java 25. We already support some post-deployment AI assistants that can be used once a solution is deployed. We as this builder, solution creator, the AI actually doesn't stop there. We built an alarm rule AI assistant and calculated field assistant that helps user continue to do some improvements or updates to their solutions by adding new alarm rules, creating new calculated fields, or modifying existing ones. All of this happens directly on the deployed infrastructure. Additionally, we added several improvements to the solution builder, such as skip interview mode, where you can bypass the interview from a BA that was introduced at the first stage in case the domain of solution is already understandable. Instead of answering the questions like your assumptions are correct, do your best, we can just hit that button and go ahead and generate the solution. Plus, we are working right now on extending our testing base with evaluation tests, trying to cover as much cases as we have. And one more thing additionally to say is that beyond the solution builder, we are actively expanding our LLM-based tooling across the platform. We are developing the CLI right now, a command line tool that will be powered by code agents like Claude Code, and that will enable programmatic management of ThinkBoard solutions directly from the terminal. We also start work on building device connectivity assistant, and that was mentioned in the paper future work section, that will automatically generate optimized transport configuration for the device. We'll be able to configure integration or data converters to connect the devices of different hardware specification. Thank you for attention and for your attention. I'm happy to take any questions.
Thank you for interesting reports, and we have a questions. Valentin, please.
Yeah, that was impressive, I would say directly. So I can say that it looks really amazing. And the first question is that BA agent, which you mentioned a couple times, how did you build that, and what kind of the skill set your BA agent incorporates?
It's a good question. We have basically multiple BAs. I have a slides and text for my slides, but then at one moment I just start describing this in the way that not go through my speech text that I have. And actually, we have not one BA, we have multiple BAs. We have solution architecture BA that actually designing the high level description of things that needs to be developed, like what kind of device and assets will be used, what kind of telemetry keys needs to be created for them. Also, like we have some kind of just string-based relations field in a schema for BA, where he describing the relations that needs to be created between different type of entities in the system. Also, we have such kind of fields that call it customer and users, which basically describe if the system need to have a customer hierarchy, or is it just tenant-only solution and you actually don't need a lot of roles in the system and you just want to connect you one device that you have. So we have a separation between a customer solutions with a customer hierarchy and so where multi roles and basically a bug control need to be added, and just the tenant-only solutions where a user just connect his device and want to see it want to create a dashboard for that. So this was like kind of features that was developed after we present our paper, but like I believe we will describe all of these details in the future work. And regarding the skills, oh, I forgot to mention that also we have like a short but structured object for metrics. So we decided that BA actually doesn't know to needs about the feature that we have in the platform that call it calculated fields. We decided that he actually need just design which kind of metrics user want to get from a raw data that are received from the devices. And because like initially we started work, we tried to make the BA directly say which calculated fields needs to be generated and provide some like high level configuration of that, and it was difficult for him. He made a mistakes, and that's why we switched to something that is more easily to understand, which we call metrics, and we have like a list of predefined metric types that are BA know. So we like have a resources file where we're describing what each metric do, how the metrics can be used. And also we have a structured alarms, like parameter in a schema that like just in a natural language describes the condition, describes the profile name for which that alarm should be triggered, and describe if I'm not mistaken, it's alarm name. Yeah, alarm name, condition, and profile name to which that alarm should be applied. So, and BA actually provides this short JSON with predefined structure, where some of the fields are just natural language strings, and some of the fields are like have some additional structure. And after that, we are sending this to a subsequent non-persistent assistant to do their work. Like we are sending customer and users to entity profiles assistants, as well as device and assets. After that generated, we are sending that to entity relation assistant and so on. And finally, we are getting a solution descriptor. About the skills of BA, we have written for him some kind of description about what he can do. I don't know how to describe this in detail, but Actually,
I
we
think
have.
the level of detail is already sufficient for me. That was more
Oh, sorry.
important to understand how you educate I mean, I don't want to take too much of a time because we still have one report and I see
Yeah.
one extra hand raised, but I will definitely look forward into your publication just to read through and then contact you afterwards. Thank you very much.
Just one more thing that I would like to mention. If you want, you can always. We already published it just a few, I think 1 week or 2 ago to our cloud, and we have a free account, and I believe that at least one solution can be created with a free account. So if you want, you can try it on your own. I can send a link if needed after presentation in chat. So
That would be wonderful. Thank you very much, Dmytro.
yeah.
Okay, thank you. And we have one more question from Petrenko Tatiana, please.
Okay. I would like to receive very, very short answer.
Sorry. Yeah,
Very, very short.
I will
And
try.
my question is, as I understood, that every change in your platform will need to using something, for example, Gemini, artificial intelligence model. If you'd like to change something in your platform.
You mean if I want to change something in this solution
Yes,
that is
yes,
generated?
Yes.
Currently, there is an advanced option where you can access the solution descriptor, which is presented just a JSON file, and you basically can edit that manually without asking some assistant to like BA or planner to do some changes. But this is available only after you get initial blueprint created by BA. So
it's question about how often we need to use Gemini if we created a stable version of your platform. It's about this question.
It's basically the idea is to build it quickly and not take a lot of time of manual configuration. After that, you can do any additional updates manually, and it's like we created this just to simplify the barrier between users that doesn't have understanding of how the platform work, and because we have a lot of different features and it's difficult to understand everything when you first time log in. So this provides you with ability to easily see the live demo of what like the system can do, and also it will be working, so you can just do additional add-ons to your solution, and it's not required Gemini at all.
Oh, thank you. I understand. Good idea using LLM for creating interface platform. It's need every time a lot of time.
Yeah.
That's a good idea. Thank you.
Okay, yes, thank you for your discuss about this presentation, and we go to the next our presentation, and next after is Mridan Khan Mandal. Are you here?
Yes, I'm here.
Okay, you are welcome to presentation.
So like I think you can see like Can
We
you
do
see
see your
this
screen.
screen? Oh, okay, thanks. So like this research work is for solving the GIL problem in edge devices. So like GIL is the global interpreter lock, which is a mutual exclusion for thread, it's a mutual exclusion device uh, for assigning threads to processes for various tasks. Like as we can see, Python has GIL for avoiding rest conditions, because like if we have multiple threads modifying the same object at the same time, we can run into some rest conditions like one thread modified the object at the wrong sequence. So like the objective is to optimize Python-based orchestration layers of AI agents on uh, resource-constrained hardware, edge hardware. And the thing is that, as we can know, OpenClaw and a lot of AI agents are currently running on many edge devices, like on Raspberry Pi 4s and 5s and on phones. So the problem is that they have a lot of tool uses, on which you have a lot of, which make a lot of threads, which leads to a problem of this global interpreter lock. Let me come to the next slide. So here's the problem of the saturation cliff. Saturation cliff is a performance degradation of greater than about 20 to 30% that occurs when we have a lot of threads, more than the specific threshold, depends on the device, depends on if it's a single core or quad core device. The cliff is triggered by GIL contention context switch overhead dominating the useful components. Like we have a lot of input output going on, input output operations going on, but like they all try to have the tasks assigned to various threads. But the problem is that if there are a lot of threads, that we have a performance, we suffer some performance degradation. There are multiple ways of already work around this solution, like multiprocessing, asynchronization, and static threading. But the problem is that single core and quad core devices, like edge devices, can't have a lot of multiprocessing because there's a lot of let's say memory overhead in the RAM, and asynchronization has a lower thread, but the entire event loop during the CPU1 data leads to serialization and not enough utilization of the compute power. So this leads to a problem of we can see saturation over it. I think you can see that almost if we increase the thread count, there's a degradation in performance. If there are some mixed CPU and input output overload as compared to the input output, normal pure input output over baseline. I think you can see the table 4 that I've taken from my paper manuscript itself. So let's talk about the operating system and GIL paradox. The thing is that operating system believes that every task should be assigned a thread in itself, since all threads are free to do whatever they were. But Python doesn't allow that due to the global interpreter lock. So is only one thread can operate on the complete its tasks at a given time, because it needs to have the Python bytecode executor itself for the modification of the object. And this leads to a contention cycle where threads rapidly wake and fail to acquire the lock and sleep again, wasting CPU cycles on context switches. Like we can see the panel A, panel B, and panel C. There are multiple cores, like a quad core device, let's say, and all of them want to have their lock on the Python bytecode to perform some tasks. The thing is that only one of those tasks can perform some useful work, because let's not just waiting for them to assign to the GIL mutex object for a thing. And I think there's also a talk about, I think I proposed a simple algorithm that solves this issue. So it has a specific parameter named flocking ratio, the beta value. which is a really simple value for which is the as we can see the equation. So T1 is the basically total time from the task when it was assigned to a thread to the completion of the task, and the TCPU is the total time when the processing actually occurred on the CPU. It's a ratio. It's a very simple ratio, but it's really useful because we can see how much time the thread is actually utilized for actual computations. And there's average, the below we can see the beta dash, which is like the average of the all of these beta values from the thread pool. We use this to like actually find out how much average time a thread pool is actually doing the computation rather than being blocked by GIL saturation or CPU saturation and contention. As we can see, there are two interpretations of these beta values. The thing is that if a beta value is high, then the threads are waiting for input-output from the sensors, and it's safe to increase the concurrency, that is, increase the thread count. But if the beta value is low, the threads have been blocked by the global interpreter lock saturation. Like we are seeing a performance degradation in the thread pool, and adding more threads will lead to more thrashing and GIL contention, which leads to like the decrease in performance. And here we have a chart which shows that the application layer, and we have three parts of this algorithm: instrumenter, the monitor, which actually observes if the GIL contention or saturation happening, and the controller, which actually handles if we are supposed to increase the concurrency or like actually maintain the thread count or decrease it. So like here's the system architecture. Here's the system architecture. The instrumenter actually measures the time T CPU and T-wall using OS counters every some specific range of time. Let's say 500 milliseconds or 300 microseconds or whatever like you want to set the time to be, and then measure calculates the beta value, the blocking ratio, and then calculate the average beta value, blocking beta value across the thread pool, and then we have the monitoring part, because we have the monitoring part involves stabilizer, which is a kind of a digital low pass filter, which I like to, which is exponential weighted moving average, EWMA, which I think you can see the recurrence relation, its recurrence relation in the black. It's a really simple but powerful tool to actually stabilize the values that we have measured, which because we have a lot of transient spikes and noise from these measurements every some specific time, like 500 milliseconds. So we use this EWMA for actually stabilizing and smoothing out the signals. I use this signal instead of like simple moving average or like let's say Kalman filter, because Kalman filter is really complex. It takes a lot of computing overhead, while simple moving average doesn't take into account that more recent measurements are more important than the past measurements. But EWMA takes that into account through like the alpha ST and the alpha parameters. The controller logic has like this decision tree, as we can see in here. It checks if there are taxes queued in the memory, and then it checks if the blocking ratio is above some threshold. If it's some above threshold, if it's above some threshold, it knows that it's some mixed CPU and input-output overload, and it's there will be a performance degradation due to saturation cliff. And then I think I just said the wrong thing. It should be less than the with saturation threshold, and then it triggers the safety veto. Like the safety veto is it decreases the thread count to actually increase the blocking ratio so that we don't have performance degradation. Else, it just scales up and increase the thread count so that there's enough computation CPU utilization, and it only performs the operation every 500 milliseconds or whatever time we like to assign it to. It's a window like, and as we can see, we have an instrumentation overhead. Like I run some studies on this, and we can see like Combat Python is like good enough. And then we have the theoretical stability and convergence part, like the theoretical part is like it's really stable or not, like this algorithm. So as we can see, like it is stable. So there are like two theorems based on this thing. The computational complexity of this controller is like O of 1 in space and time complexity, which makes it have really less computational overhead while calculating it. I think in the RAM, it takes about less than 2 MB as compared to multiprocessing, where it takes over 150 MB or 200 MBs, which is like nearly 100 times more. Like in theory, practicality, but in theory, like it's O of 1. So like this algorithm is really good. About the theorem, like under sustained load, the sequence of thread counts is non-decreasing until it reaches a safety boundary. And then there's a convergence theorem that a system converges to a stable operating point that maximizes the throughput without violating the GIL safety threshold. And as we can see, there's a visualization of this theoretical stability. About the evaluation and results, the system achieves about 96.5% of the optimal performance without actually tuning it. The optimal performance when all of the tasks are assigned threads and all of them perform those tasks in the threads without actually having thrashing or having a long wait time. The algorithm is efficient at 93.9% average percent efficiency across 7 edge AI profiles. Like I ran through vision pipeline, voice assistant, sensor fusion, RAG calculation, SNF inference, and edge analytics, and ONXX. Like all of these are simulations, but it shows that it's efficient algorithm which managed to reach near the optimal thread count without actually tuning or assigning the threads. And as for the code, like the code has been released to the GitHub. It's in the library named Vitapool. I've also done some evaluation studies comparing other strategies for like assigning tasks to the threads and handling the thread counts like thread pool, process pool, asynchronous, and queue scaler. And as you can see, there's the results. So that's like it. So like, thank you for the like presentation, like hearing my words. Any questions?
Okay, thank you for your presentation. And we have a question. Valentin, please.
Yeah, thank you very much for the presentation. And the first question is, the presentation defines the saturation cliff as a performance drop of more than 20% when the thread count exceeds to this a certain threshold. In the single core experiment, and what counts does the cliff occur, and how large is the performance loss in this case?
In single core configurations, it like depends upon like it depends upon like the device and what kind of workload you are running. Running, but as per the experimentation, yes, the degradation is about 20 to 40%, and the thread count is roughly around, I think, about 1,000 threads or something like that.
You mean this is the very bottom line, about 40.2%. Okay.
Yes.
And the second question is, what is the blocking ratio beta, and how does that develop? How does a developer interpret a high beta value versus a low beta value when tuning this, when they are tuning their system?
Yes, that's a good question. Like the beta value is like a simple ratio. It's as we can interpret it as the average amount of time which the task is actually performing using the CPU or performing computations while assigned to a thread. And for a developer, low at beta value shows that the thread is really efficient and spends most of its time executing the code on the CPU, while a high beta value, like when it approaches 1, because it's a 0 to 1 value, indicates that the thread is mostly ideal or it's most spending its time in context over switch and thrashing.
Thank you. And last question. It's already too much. The controller requires 3 consecutive signals before scaling the thread pool up or down. What instability or failure scenario does this hysteresis mechanism prevent?
This like
That's the one.
can you again repeat the question?
Yep. What instability or failure scenario does the hysteresis mechanism prevent?
Yes, the stability of the hysteresis mechanism is like that. It requires 3 signals before scaling to ensure stability, like because when we have transient spikes, like when there's a lot of noise when measuring the beta value, it tries to like not immediately respond to the spikes, like because it will lead to constant scaling up and down of the thread count, which leads to more thrashing. So it has 3 consecutive signals before it scales. So like even if there's let's say a constant spike in noise from the beta values, it will not like immediately switch scale up or scale down the thread counts, which leads to like better performance. And
Thank
the
you very
failure.
much. Thank you.
Okay, well, thank you for your presentation, for your answers and your questions and this discuss of our workshop. We truly thank everyone for participating in our workshop. And now we ask everyone to turn on the cameras for group photography. Please don't share your screen. Reading can.
I'm not sure how to like turn off this. Is the screening sharing turned off?
Well, thank you. And now please turn on your cameras for group photography. Okay, thank you. And we invite all of you to participate our next conference and our next workshop. And have a nice day. Thank you.
Thank you.
Thank you for you. Thank you for
you.
your organization.
Bye.
Very good organization. Thank you.
Thank you. Goodbye.
Bye. Bye.
Bye-bye.
Bye.